So let's take a deeper look into Secure Sockets Layer, or SSL. This one goes way back, originally developed in 1994 by the good folks at Netscape Communications. These guys tackled a lot of difficult challenges for all of us, and we really wouldn't have what we have without them. We didn't have e-commerce until SSL came along, and when it was first implemented, a lot of folks were using 128-bit encryption, and I remember, like in France at the time, it was illegal. They said you can't use encryption that's that strong, the government doesn't know how to break it, yet web browsers were being rolled out left and right, they were being strengthened, it kind of put everybody in a weird situation. We're even in scenarios today where using amateur networks, encryption isn't supposed to be used. So this takes us way back. These folks solved a lot of problems, they got us to where we have e-commerce, they changed the world, and then somehow went out of business in the process. So SSL was really their baby. They left off with SSL version 3, which was technically proprietary because it was built by Netscape, and the whole world was kind of using it. SSL version 3 became standardized in TLS. So SSL version 3 was basically rolled into TLS version 1. Today in 2020, the current version is TLS 1.3. This is fairly recent. A lot of folks out there are still using TLS 1.2. So technically, remote access SSL VPNs are really using TLS, not SSL. SSL is susceptible to some other attacks that TLS is not. So when you're trying to do man-in-the-middle, one of the techniques it will do is downgrading encryption. They abbreviate that DLE, downgrade to legacy encryption. And if you look at some of the attacks, like the Poodle attack and the Golden Doodle attack and the Zombie Doodle attack, I got a Labradoodle, so I get excited about all those. They're really just saying, let's get in the middle of the communication. And remember, before you can do encryption, you have to talk about how to do encryption. So party A is talking to party B, and it says, hey, why don't we do AES 256 with digital certificates and let's do the most secure encryption we can. If there's an attacker in the middle, he'll swat that down. He'll say, I don't support it. What else do you support? And basically, when you're trying to initiate a tunnel, you offer these proposals. You say, here's the best way that I know how to do crypto. Do you accept it? And you have to agree upon a proposal before you can authenticate. Isn't that wacky? So you don't know who you're agreeing with until you agree. And then once you agree, you perform the authentication. So downgrading to legacy encryption is where we go out, hop in the middle of a connection with the man-in-the-middle attack. When we see proposals come in, we swat them down, and then eventually your oldest, weakest proposal is sent across. And we go, that would be easier to break than some of the other proposals that you've sent, so we'll go ahead and pass that through. Kind of neat. So that's just something that we've used a bit in the past. Looking at SSL and TLS, they're both designed to basically do the same thing, and that is authenticate the client using an X.509 certificate. And we can also authenticate the server using an X.509 certificate. So ideally, in a perfect world, we're going to authenticate both. If you're just getting this up and running, if you're the administrator that's already outgunned and outnumbered and under budget, and you're just trying to keep your head above water, you're probably not going to roll out client certificates right away. We would authenticate the server to the client using a certificate, right? They're coming across the internet, I get a certificate from a public CA server, everyone trusts it. That's half of the problem. How do I authenticate the server to the client? Now that we know the server is who it's supposed to be, we can authenticate clients to servers. You can use X.509. A lot of times we'll use Active Directory, just using usernames and passwords, but you can also use digital certificates to authenticate against AD. We can select common cryptographic algorithms and generate our shared secret. Again, we start off with asymmetric encryption with the goal of getting to symmetric encryption because it's so much faster and so much easier. Once we've got our shared secrets, once we've agreed on how to do crypto, we actually do some crypto. So we'll set up our tunnel and we'll pass traffic back and forth. TCP is what's going to be used natively, but UDP has less overhead, and in the event that a packet is dropped, TCP retransmits. But you've got TCP for your VPN client, and you also have TCP for the application, such as remote desktop or SSH, which if you're using TCP, you get 2 retransmits. If you're using UDP, beyond the lower overhead, you also get the single retransmission. So DTLS tends to be more efficient as a transport. The downside, again, UDP 443 not always allowed through. So Cisco AnyConnect supports DTLS, and it's going to try to use it when possible. We go ahead and we set up our TLS tunnel, and we try to pass traffic through DTLS. If we don't get confirmation, well, then DTLS fallback. That is, just go back to using regular SSL or TLS, which is going to happen over TCP 443. Don't forget that intermediate devices need to support TCP 443, which is an easy one, but it's a UDP 443 that a lot of folks forget about. So again, just to touch upon DTLS, it's an alternative VPN transport to TLS using TCP. As far as the security, it's not any different. This all comes down to the security association that you negotiate. You're going to agree upon how to do crypto. So AES, SHA, they're still being used. We're just talking about what's the transport. If it's ESP, there's no port number. With TCP and UDP, we do have port numbers. That's really all that it comes down to. The goal of DTLS is to mitigate latency and bandwidth problems. Think about it. If you're on a network that has packet loss or that has a weak signal, every single time you drop a packet, you send 2 more. So every time the network gets bad, it gets worse. That's not great. With DTLS, we can escape that situation. Again, if there's packet loss, we only have the single retransmission. And again, if it's enabled, this is going to take precedence over SSL. This is what the AnyConnect client would prefer to use. As far as SSL session and key management, there's a few phases here. Basically, the client initiates the connection to the server. It can't work the other way around. Once you get there, the server has to authenticate. That's part of SSL. It's just like if you go to Google. If I type www.google.com, I'm going to see that it connects over HTTPS. Google has authenticated to me. I didn't have to authenticate to Google. Now, the client authentication is optional, but for VPNs, it's something that we tend to do. We need to know who that user is so that we can assign them the appropriate portal. Here we see the SSL handshake. And basically, the client sends a hello across. And the server says hello. And then the server sends its certificate. This proves the authenticity of the server. He says, this is who I am. VeriSign says that I am really vpn.mydomain.com. Who the heck are you? By the way, that's all I had to say. Well, the client needs to authenticate. It could authenticate using a username and password, or it could use a certificate. Here we are with our certificate. Here we are with the client key exchange. Here we go with the verification of their certificate. Here we're negotiating the cipher suite that we want to use. And then we say we're done communicating. If this side agrees to the cipher suite, we're now finished. So assuming that we've negotiated an agreement on how to perform crypto, we can now carry data from one site to the other. So again, starts off with our handshake. We negotiate the cipher. Now we can pass our HTTP data back and forth. The data is actually going to be partitioned into records, and each record, as they call it, is going to be protected separately. So we bring in the record, it's going to be encapsulated, it's passed to the other side, it's decrypted, it's reassembled. Each record consists of the following: the header itself, which says it's kind of like an envelope, the data, this is what goes inside of that envelope, and then finally our integrity check. Remember that hashed message authentication code not only does the integrity check on the data to show that it has not been altered, but additionally authenticates the device that sent us that data.